So with the group so far, we've worked on um, making raised beds. So we've worked with them here at the government site on field layout, field design, talking through that. I visited each of their farms, talked through their goals, what they'd like to do, how they want to do it. So we're putting together plans to do 1 or 2 projects on each of their farms, kind of help them out, get the class there to learn at the same time. We've been to a couple student farms already for a few different workshops. Bokashi uses effective microbes, a specific set of microbes to do basically pickling style composting. What else? We went to another farm to work through how he does his production. So he's a little further along than others. So we talked through his growing scheme, how he produces plants, where he delivers. We're going to keep visiting that farm. We've planted a plot. So we'll keep visiting over the next couple months to kind of work with that plot and keep learning with the class.
Yeah.
We've done a compost extract. Been waiting on materials from the States to do kind of some different shade house things, bringing a caterpillar tunnel. We want to start doing composting a lot more, but we're not going to wait for the thermometers. We're going to try to do it a different way. So we're going to start doing composting soon. What else, you guys?
Biochar.
Biochar, of course. Yeah, we've been making our own biochar and turning waste into something useful. So starting to use that, incorporating that into a few beds, a few farms. Plastic mulch. So using the plastic landscape fabric as a weed barrier, a way to smother weeds, hold in moisture. They don't have a lot of organic matter to work with to start off with, so it's kind of a crutch for the first few years to get going until they can generate some more of their organic matter in their soil or create a mulch of their own. Compost tea. Yeah, we made some extracts. I've been talking a lot about Elaine Ingham and played a few of her lectures to the class. So kind of prepping them for the soil section, getting them ready to understand a bit more.
Okay. All right.
Anything else, guys? That's it? Yeah, I think that's it.
All right. Why don't we go around the room real quick and just have everyone just say their name, and we'll go from there. And how many do we have in the room there? 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah. Why don't you guys come up to the computer and just say your name, introduce yourself to Jim real quick, so I don't repeat. They're just going to come up and introduce themselves.
Yeah, microphone work better.
My name is Richel Alberto.
You want to tell them about your farm, what you're doing a little bit?
At home, I have planted a farm. By the time I do not, because I don't have enough water. Okay. Thank you.
Okay.
My name is Shastri. I'm doing a project for the government. It's a permaculture project. So that's why I'm doing also this course to learn more, understand more, so I can apply it on a small farm.
Okay, sounds good.
Hi, I'm Senelio. I've been doing home farming for about 10 years. doing and also teaching. And right now it's time to go to the farm, go bigger.
Okay, very good.
Celio is also one of the mentors that's helping me out.
Okay,
Hi, my name is Joshua. I run a diversified vegetable farm, organic farm, and I also have a farm-to-table restaurant. And we also run a 30-member CSA, and I just feel the need to learn more about what I'm busy with.
okay, sounds great.
Hi, my name is Aisha Marchena. I have been doing landscaping for the last 10 years. And now for the past few years, I'm doing farming at my farm.
Okay, very good.
Hi, my name is Roland van Reenen, and I'm doing some permaculture research and educational projects for government also. And I'm one of the mentors also. Nice to meet you.
Okay, very good.
Hi, I'm Henry Barbolina. They call me Barba. I have like organic farm of about 2 acres and specialized in aquaponics.
Hydroponic, okay.
My good afternoon, good night. My name is Melinda Rosalia Stasia, and I want to do more about awareness. I have a farm. I have not so much water, and I want to know more about water management, and as well about nutrients, because I want to teach people that they have to be more conscious about the soil. And as I have been, working on the farm for about 8 years. I started with sorghum. With sorghum, it's not so productive because of the lack of rain the last years. So I started to doing more about permaculture, and I am creating a food forest.
All right, very good.
Hi, good evening. My name is Eric Alberto. I have a little farm that I plant my own plants. Plant. I come to learn more.
Okay. Okay.
Hello, my name is Julian Juliana. Normally, I used to plant with insecticide, and I'm new to learning about to plant with. You laughing again? Yeah, I'm planting to learn about organic.
Strong and sexy also.
Let's
tough to follow.
Hi, I'm Liliana, and chicken. I do planting too, and I follow them on. Thank you.
Okay, very good.
All right, Jim, that's them.
It's a group.
Yep. There's a few
All right.
missing this evening, but yeah, that's the bulk of them.
All right. All right, very good. When we get to the outline, Chris, that I put up there, I may have you read some of the points and then I will comment about them.
Yeah, sure.
It might be better that way. But we'll try both ways. I'll make a few general comments. It's my pleasure to be connected to all of you today. Most people refer to me as Dr. Jim. My granddaughter calls me by a wide variety of names. But I grew my first organic crop in 1971. So I've been involved with organic agriculture for 47 years. When I grew my first organic crop, I was a university student studying agriculture. On my father's farm, I was introducing organic agriculture. He did not have any idea what I was doing. But nonetheless, we planted our first organic farm, my first organic crop at that time. Since then, I obviously have gone into the academics of agriculture and the industry of technology development for organic agriculture. For the last 37 years, I've been the principal owner and president of a company that's involved in manufacturing pesticides and fertilizers that are used in organic agriculture, including insecticides and nematicides, bactericides, herbicides, and as well as microbiological products. We have laboratories in Iowa next to MUM and are a big supporter of the agricultural initiatives at our university in Iowa, and have been helping with their agriculture projects from 1980 up to this date. We've done many projects over those years. This is kind of a fun project for us. I'm currently in Bali, and I just gave some lectures at Udayana University on the topic of global development of low toxicity plant protection. This is a topic of great interest around the world today. There is a need to reduce toxicity in food. And in your country, while you are reinventing agriculture in your society in many ways, which is a common thing on many of the islands in the Caribbean. As you know, a lot of the islands in the Caribbean relaxed their initiatives for or agriculture in general in favor of tourism. And the islands that I have visited, the members of the various ministries of agriculture on the islands have, in many cases and quite often, expressed a great interest to reestablish agricultural industries on the islands so that the islands are not totally dependent on tourism. Does that make sense? Have you heard that there in your area as well?
Yeah, they're all very familiar with that idea.
Yes.
There's also an oil refinery here, and the government
oil?
Yeah. And the government has very purposely turned away from agricultural development, depending on which political party is in power.
Yes, this is an issue. It does not help to force the country or to favor the requirement to import your own food. Be better if you were able to produce your own food as much as possible. And the visitors who came to us from your island, they reported to us that a pretty large percentage of your food is imported. Chris, do you remember the actual number they were using?
I mean, it's like 95%, something like that. Yeah, something around 95%.
All right. Well, here we have a small group of a dozen people, and your job is to reverse this trend. It's a pretty big job, and I congratulate you on taking on the task. Would you say on the island that that you have a feel for how many people are actually farmers today? If you just had to make a wild guess, what percentage of the island would say to us that they're engaged in agriculture on some level? 5%, 10%?
Not even 5%.
Oh my.
1 to 2%.
Okay. 1 to 2%.
Maybe.
Okay. And
apparently most farmers are very old, 70 to 80.
70 to 80.
Yeah.
Well, there's nothing wrong with being 70.
You would say that, wouldn't you, Jim?
Yeah, I would. I'm a lot closer to that than I am your age, Chris. But I'm an old farm boy from Illinois, and Chris is a young farm boy from Iowa. And we have grown up in an agricultural society and an agricultural economy. And understanding agriculture is something that kind of gets into your blood. It's something that often you inherit from your family members. You know, I obviously went through university training in agriculture all the way through PhD. But when I go around the world for the last 40 years, participating in projects in Latin America and the Middle East and Asia, Europe, United States, I often tell people that although I have a PhD in agriculture, half of the knowledge that I use, I actually got from my father and my grandfather, who were all farmers. So I would be willing to bet that a lot of the information that Chris is prepared to pass on to you, he got a large percentage of that from his family. That sound about right, Chris?
Yeah. Building a fence is building a fence, whether you're organic or not.
Absolutely.
Yeah.
Driving a tractor.
Yeah. I have stories from my dad saying pretty much the exact same thing even. So.
Yes, that's it. So, you know, we learn a lot generation by generation. And, you know, there is a chance that in the islands, in the Caribbean, some of that tradition has been lost. And you haven't had an opportunity to learn from your previous generations. Even in the U.S. today, the number of young people who can say that they have a connection to agriculture has gotten to be very, very small. We have young kids who really don't have a clue where their food comes from. And if you try to explain to them that milk actually comes from a cow and doesn't come from the supermarket, it can be a challenge in urban societies today. And the U.S. has become progressively more and more urban. So people like Chris, people like myself are in minority. We're becoming more and more unique. When you went through high school, Chris, what percentage of the kids grew up on farms?
Gosh, I don't know. I mean, 1%, 2%. I mean, we had our high school had 650 people. We probably had, I don't know, 30 people maybe in FFA, max.
Okay.
Maximum.
Yep. Yes. Well, I went to a much smaller high school many years ago, and the percentage of us in my class that probably grew up on a farm was pushing 15-20%.
Wow.
Yeah, so that's that's a different contrast. Of course, this was a rural high school. It was pretty small. A lot of us were growing up on farms, and but the interest in becoming a farmer was not so great. Chris mentioned FFA. When I went through school, when I went through high school, we had what was called the vocational agricultural studies. And in the class for vocational agricultural studies, we were given the option to join a club called Future Farmers of America, FFA. And that club still exists. It's one of the largest clubs in high schools all through the United States. The state of Ohio, one of our states in the US, the state of Ohio, at the high school level, it has 25,000 students, 25,000 students who are members of the FFA. So it's a pretty big number. It's still a very large club. When I went through, we were being trained to become farmers. In your high school, in your country, it would probably be a good idea to introduce the training, vocational agricultural training. I think that could be very helpful in creating a future for agriculture on your island. Of course, you have to start somewhere, and you're all the guinea pigs. You're the beginning of it. And from this seed that is represented by your class, we hope to see an agrarian culture come to life again for the island of Carousel, so that you begin to produce the food for yourself. The food that you produce will always be far superior to the food that you import. My purpose today is to give you an introduction to soil science. And this means, in this case, soil chemistry and soil physics. It's an interesting thing when you approach the science of agriculture, you immediately employ the sciences of chemistry, physics, and biology. And to a large extent, everything that is involved in agriculture revolves around the concepts that are represented in the science of chemistry. So when you think of soil, you should think of chemistry. When you think of plants, you should think of chemistry. When you think of fruits and vegetables, you should think of chemistry. Farmers are applied chemists. They're working with chemicals in order to produce a result. Everything about the function of a plant, the physiology of a plant. Physiology means chemistry of a biological system. So in our talk today, we're going to connect a lot of the discussion about soil science to the field of chemistry. So in this case, it is the existing chemistry that is in the soil, as well as the chemistries that you introduce to the soil, and the end product, which is a metabolic, the result of the metabolism of plants, is the result of the chemistry of plants. The food that you wish to produce, the food that you do produce on your farms today, whether you're working with soils or you're doing it hydroponically, is a byproduct of how you manage the chemistry of agriculture. Okay, having said that, let me outline how we're going to do this. We're going to cover some basic introductory level material on soils. We're going to primarily focus on soil chemistry in this presentation. We're going to take our time. If you need to stop and ask a question about any aspect, any main point that we're presenting, feel free to stop me at any time. Chris, you can help with that, and we'll make sure we get that done. The topics that I will discuss will include the measurement of soils, the characteristics of soils, the fertility of a soil, and then we will move from there into the utilization of nutrients or plant foods by a plant. And then we will shift to soil physical properties, sometimes called soil physics, but it's really the physical properties of a soil. And in that section of our introduction to soil science, we will talk quite a bit about water, the dynamics of water in the soil, the dynamics of air in the soil, the management of structure in soil, and the texture of a soil. And that will be the second phase of our introduction to soil science. Okay, so first thing I'm going to do is open up this outline. Chris, you have shared the outline with them electronically, is that right?
Yes, but most of them can't access it right now.
Right, yeah, I can see that.
Yeah.
So when we put up the main points, will the people in the back of the room be able to actually see the text? And I guess maybe even if they can, we need to read out the text so that we all are focusing on the same thing and they understand each point as we go through it. Is that okay?
Yeah, sounds good.
All right. The way I would like to do this is just read out each point. The points are very brief, but each paragraph is a different point. And these points are really a composite of summarized information that you need to have to understand in this case, the science of chemistry in soil science. So we'll start with the more elementary part of the presentation. Let me pull up my sharing here. All right. That's how I do this? Yes. Okay, you can see that?
Yes.
All right, let me push that up to higher resolution. How's that? A little better?
I think so. You can see in the back? Just a little bit more.
Okay.
Let's try that. There we go.
Okay. All right. So I'm going to play a clip for you. I've got several clips to integrate into the conversation here today. All right. I have to get used to navigating in this thing.
Getting it, Jim?
Can you see it?
No, I can't. Maybe if you minimize the introduction to soils outline.
Okay.
Still just seeing the outline.
Yeah. Okay, okay.
I could potentially play it on my computer and share my screen, or just put my screen up on the overhead.
Okay.
Want to try that?
Yeah. I think I have to play it from within Zoom. It doesn't just automatically share my, well, it should share it, but it's not doing it. You're still just seeing the outline. Okay.
Yeah. I think I can bring it up here.
Welcome to the Science Basement, your source for videos that are entertaining and educational.
Come on. There we go.
Today, we are talking about one of my favorite subjects, which is soils. I love soils. I really hope that you'll love this video and continue on my other videos about soils and other science subjects. One of my favorite songs growing up was Dirt You Made My Lunch by the Banana Slugs String Band. Many of you probably haven't heard this song. I really encourage you that after you watch this video that you'll continue on and listen to their song. And the great thing about them is that they're right. Everything comes from soils. Our food, our clothes, the dyes that color our clothes, and ultimately all the fuels that power our vehicles and our cities, everything can be traced back to soil. So that brings me to my next topic. While the Banana Slugs did get a lot of things right, this is not dirt. It's soil. This is dirt. It drives me crazy because I think people use these interchangeably, but there is a difference between soil and dirt. The best way to think about dirt is that it's displaced soil. It used to be soil and it came from soil, but it was moved somewhere that it shouldn't be, like your clothes or your shoes or your carpet. Soils, they're a little bit harder to explain, and so that's what we're going to do right now. One of my favorite quotes about soil is from Hans Jenny, who is the forefather of modern soil science. He said that it is embarrassing not to be able to agree on what soil is. And he's so right because everyone explains soil a little bit differently, and it means different things to different people. Engineers and people involved in construction, they think of something that's moved around by equipment and whether it's suitable for certain construction projects like houses and roads and other big buildings. Geologists think of soil as it's just a temporary phase in the global rock cycle. It originally came from rocks and it's soil now, but it will eventually become rock again. Farmers and other people who are involved in agriculture think of soil primarily as a medium for plant growth. It supports roots, it provides nutrients and water, and helps plants grow upright. There's been a lot of debate about soils recently, I think in part due to the recent NASA missions to Mars. Scientists have been discussing whether Mars has soil, or is it Martian soil, or is it fair to even really call it that? My definition is that soils are the mixture of minerals, organic matter, and water that can support life. So according to this definition, do you think Mars has soil? This is a really, really tricky question. So let's go over it together. The key word here is life. I think under the right circumstances, Mars could support life. I think it's fair to talk about Martian soil, but it's just important to remember that it's different than the soil as on our own planet. The amazing thing about soils is that they're in an interface zone. And what I mean by that is that soils are at the interface of the atmosphere, the lithosphere, the hydrosphere, and the biosphere. Anytime that you're at one of these interface areas, there's some incredible diversity of life. Think about the middle of the atmosphere. How much life is there? Or what about the middle of the lithosphere, or even the middle of the ocean? Amazingly, there is life, there's just not very much of it, and there's not usually very much diversity. However, when you're at an interface area, there's a lot of diversity. I like to think of coral reefs. They're a great example because they are at an interface between the ocean and the atmosphere and land, and there's an incredible amount of diversity. There's lots of other examples like rainforests and even grasslands. So soils are at a permanent interface. No matter where you go, soils are always in between the atmosphere and the lithosphere, or the hydrosphere and the biosphere. So naturally, there's a lot of diversity. We all know that soil comes from rock originally, but how do you get from this to this? The key word is weathering. Weathering basically means the breakdown of rocks into smaller and smaller pieces, and that helps make up soils. Weathering can happen in several different ways, and one of these ways is physical breakdown. Anytime you have rocks that crash into other rocks or fall down, small pieces will break off and contribute to soil formation. Another big player in weathering is water. Raindrops falling on rocks and other surfaces, and also the movement of water, can contribute to soil formation by dislodging small pieces of rock. Think of how the Grand Canyon was formed. It was formed almost entirely from water. All that rock that used to be there is now soil for someone else. Another contributor is temperature. Rocks actually expand and contract depending on the temperature, which can cause small cracks to form. If water gets into these cracks and freezes, it will expand and continue to make those cracks larger and contribute to soil formation by breaking the rocks into smaller pieces. So those are a few examples of how rocks can turn into soil, but there are also other factors that control the rate of soil formation. These are called the 5 factors of soil formation. They are climate, topography, time, parent material, and biology. Differences in these 5 factors can speed up or slow down soil formation. Climate plays the largest role in soil development. And it's also really important to remember that climate is not weather. Weather is what's happening outside right now, like whether it's cold or whether the sun is shining, but climate is the average weather for an area over at least 30 years. This can be seasonal changes in temperature, how much precipitation an area gets, things like wind. They all play a role in how fast or slow soils develop. When you think of arid climates, they're usually very dry and there's not a whole lot of life. Soils in those areas take a very long time to form, and they're very sensitive. And what soils do form are usually very thin and rocky. In contrast, when you think of other areas that get more precipitation, soil development usually occurs more rapidly and soils are deeper. Another factor that affects soil formation is topography. Soils are usually thinner on mountains and hills and deeper in valleys and depressions. This is usually due to the movement of water, which carries soil particles down and into these depression areas. Time is pretty straightforward. Going from rock to fully formed soil can take thousands or millions of years. Brings me to another important point about taking care of our soils, because if we make soils disappear or we damage our soil in any way, you will not be able to fix that problem in your lifetime, or likely in the lifetimes of future generations. Soil is not a renewable resource, so take care of the soils that you have. Parent material is another. Parent material is the rock that the soil originally forms from. This can be rocks like sandstone, limestone, other marine sediments, or even volcanic rocks. These all affect how susceptible certain rocks are to be broken down into smaller pieces, because some rocks are harder than other ones. The last factor is biology. If you take a close look at soils, you'll see roots, insects, fungi, bacteria, and so many other things, and they all contribute to soil formation because they break rocks and soils into smaller and smaller pieces. So that's it for this first video. I hope that it gives you a little bit more appreciation for what soils are and how they form and where they come from. And I hope that you'll continue on to my other videos about soils and science. Science is all about asking questions, and I'd love to hear from you and help in your learning experience. If you have any other suggestions for videos you'd like to see, please let me know. And of course, please subscribe to my YouTube channel below. That way you'll be...
Okay. Okay. So Chris, I've got another clip here, and I think I can share it now. Let me try it.
Yep.
So these are pretty elementary steps in approaching soil science. It's obviously very graphic, the way this guy presents his case, so it can be somewhat entertaining, and in 15 or 18 minutes, you're going to get a very brief, intensive introduction to the concept of soil science. All right, I'm going to play the second one.
1 second, Jim. I'm having a little issue expanding your screen. Come on.
Do you see the new one?
Trying to expand your screen to full screen, and it's let's see. Yeah, I see it. I see what you're trying to share. I just can't make it full screen yet.
I can do that here.
No, as in your player, your screen is small on my screen.
Oh, I see. Well, let me try turning it on and quickly expand it. See what happens.
What is going on here? Why can't I just do this? We're not hearing it, Jim.
I stopped it. You're not hearing it.
No.
Okay. I'm hearing it myself.
Why don't I just play this one too, just to facilitate?
All right.
Welcome back to the Science Painting and Educational. This is part 2 on a series of videos about Introduction to Soils. How many of us really understand what soil is? I want you to imagine for a moment that you reach down and pick up a handful of soil. Do you really know what you're holding, what's in it, what it's composed of? Most people think of soil as really being just solid material, just crushed up rocks that are really small. But in reality, that solid portion or that mineral portion accounts for less than half of that handful, only 45%. The remainder of what you're holding is in equal parts of water and air. Each is about 25%. And lastly, there's usually an average of about 5% organic matter. Within that mineral fraction or the solid fraction of the soil, there are different particle sizes. And I'm sure these terms will be familiar to you. There's sand, silt, and clay. These particles are defined by their different sizes. Sand ranges in size from 2 to 0.05 millimeters, silt from 0.05 to 0.002 millimeters, and clay is anything less than 0.002 millimeters. It's really hard to put these into perspective because clay particles are so small. In fact, over 50 million of the biggest particles of clay could fit in a single grain of sand. It's really hard to put that into perspective. So let's take a look at our own solar system. The sun has a diameter of 864,948 miles. It's huge. Now, when you look at that compared to our own moon, the moon has a diameter of about 2,159 miles, and 64 million Earth moons would fit inside the sun. So, if the sun was a grain of sand, then some of the largest particles of clay would be about the size of our moon. I really hope that puts into perspective how small clay particles really are. The different ratios of sand, silt, and clay make up the texture of the soil. Soil scientists use this texture triangle as a way to classify soils based on the different ratios. I know that this texture triangle looks a bit scary at first, but really it's not that bad. The best way to learn how to use it is to practice. Look up some texture triangle pictures on the internet and try it out. There is no one best component. In fact, anytime that you have soils that consist of too much sand, silt, or clay, you tend to have problems, whether that's problems with nutrients, water, or something else. The best soils have a good mix of all three and are called loams. As we go up in scale, we have soil structure. Soil structure is how the soils arrange themselves. So the particles will stick together and form what are called aggregates. And you can have several different kinds of aggregates that form. The first is no aggregates at all, or single grain. So each individual soil grain is by itself. They're not glued together in any way. Then you can have granular structure, which are small groupings of soil particles. Blocky structure is usually larger and has bigger cracks in between the aggregates. Then you have prismatic, which form almost column-like structures in the soil. And one of the worst is platy, when the soil will form aggregates that are almost like plates stacked on top of each other. And these soils are very bad about letting water infiltrate into the soil and about allowing roots to really penetrate and grow down. Aggregates can form in several different ways, and they're primarily formed by living organisms like soil fungi, bacteria, and plant roots. They exude materials that glue soil particles together. Aggregates are very important for soils because they can help prevent erosion, make nutrients more accessible, and allow water to infiltrate into the soil more easily and make water more available for plants. Moving up in scale again, we have what's called a soil profile. A soil profile is a bit like a mugshot for soils because it allows you to see the different layers. Each layer has a name, and they're called horizons. The very first layer or horizon is the O horizon. This usually isn't considered soil yet, and in fact, the best way to think of this horizon is as organic matter. It's typically composed of decaying plant material like leaves, roots, and sticks, and is typically characterized by a dark color. The next horizon is the A horizon, and this is what most people know of as topsoil. Again, it has a darker color because of the addition of organic matter from above. The next layer below the A horizon is the B horizon, which a lot of people call subsoil, but in reality, it's called a zone of accumulation. This is where materials like clay collect in the soil profile from the movement of water downward. The next horizon is the C horizon, and this horizon is typically characterized by a lighter color, maybe even an increased presence of rocks, and in a lot of situations is known as the parent material, or what the soil originally formed from. In some cases, beneath the C horizon, you can have the R horizon, which a lot of people know of as bedrock. When the bedrock is present in the soil profile, it would be called the parent material, or the material that this soil originally formed from. And of course, there are many, many different types of soils. Just imagine going on a road trip anywhere. It doesn't even need to be across the country. It could be within your own state or your own city. You'll notice soils that have different colors or support different plants, or just have different qualities in general. At the very top of soil classification or soil taxonomy, there are 12 soil orders: alphasols, andisols, iridosols, entisols, gelisols, histosols, inceptisols, mollisols, oxasols, spotosols, ultisols, and vertisols. They all have different qualities and form in different areas. While knowing these different soil orders could be useful if you have a career in soils, ultimately I think the biggest take-home message is that there is variability in soils. They vary spatially. When you look at a map of the United States, you can see that there are different regions where these soils are found. And even within a state, there could be many different types of soil orders found there. At a local level, within each soil order, soils can be further broken down into soil series. In Kansas, for example, you might find the Eudora silt loam or the Summit silty clay loam. If you're curious about the different types of soils that can be found in your area and their qualities, the best place to find this information is the NRCS Web Soil Survey, which is available online. Because soils are variable, you want to do what's called soil sampling before you plant a garden or before you farm. A lot of times, if you're standing in your yard or a field, the soil that you're standing on could be completely different than soil that's just a few feet away. The sample soil uses what's called a soil probe, which is basically a pole with a hole at the end and a bucket for the soil to go into. The hole at the end is sharpened, and as you push the probe into the soil will enter the bucket and be held there. The soil that enters the bucket of the probe is called a soil core. The depth you need to sample to depends on the nutrient they're looking for and also the lab that's going to be processing these samples. Most of the time, a 6-inch sample is sufficient. However, if you're sampling for a farming operation, a lot of times you'll need to sample down to 24 inches because you'll be looking for nitrogen, which is a mobile nutrient that can be found deeper in the soil profile. So how many samples do you need to take? This is a function of statistics, because the more samples that you take, the better that your samples will represent an average of the field. Usually it's recommended that you take about 12 to 15 cores and mix these together in a bucket to make what's called a composite sample. If you're sampling down to 24 inches, you want to separate these out into 2 different composites and have 2 different buckets, one for each. In one bucket, you'll put the 0 to 6 inch samples. Again, you'll have about 12 to 15 cores, and you'll mix these together. And then the other bucket will be for your 6 to 24 inch sample. You'll send these composites to the lab individually. Why would you need to do this? Well, in the 0 to 6 inch sample, you're looking for different nutrients like phosphorus and potassium, which are non-mobile nutrients. But nitrogen, since it's mobile, will be found deeper in the profile. If you were to calculate phosphorus and potassium concentrations based on a 24-inch sample, your concentrations wouldn't be right, and your fertilizer recommendation would be wrong. When it comes to actually soil sampling, there are 3 different methods that you can use: whole field sampling, zone sampling, and grid sampling. There's no one best method. It really depends on the field that you're sampling and what you're really looking for. Whole field sampling is best when you're looking for an average for a whole field, like when a field doesn't have very much soil variability. For this type of sampling, you'll take 12 to 15 cores at random through the field, usually in a W-shaped pattern. You'll then take these 12 to 15 cores and composite them into a bucket and send them to a lab. Zone sampling is best when you know that there is some variability in a field, like where one side of the field might be different than another. This could be for several reasons. One could be that you know that there's a difference in soil series between one side of the field and another, or it could be differences in topography, or because one side of a field has ponding or water issues. The idea with zone sampling is that you'll know that you want to treat these areas of the field differently. So to do a zone sampling, you'll first identify zones in a field. These could be as many zones as you want. and then in each field you'll take 12 to 15 cores at random following a W-shaped pattern and composite them together for each zone and send those zone samples separately to a lab. The last method is grid sampling, which is the most precise, but it also requires the most amount of time and can cost the most amount of money for soil analysis. Grid sampling is especially useful if you want to make a map or do precision agriculture. To do grid sampling, you overlay a grid on your field. Each square can represent any size of your choice. It could be 1 acre, 2 acres, 5 acres, 10 acres. It all depends on the resolution that you want in your map. Then you go to each intersect in the field, and then in a 10-foot radius around that point, you'll take 12 to 15 cores at random and make a composite sample. Just in this example alone, you'll have 42 different composite samples, which would represent about 630 cores. So you can imagine how this would be very time-consuming and also very expensive when it comes time to have a lab analyze all of these soil samples. The benefit of grid sampling is that it allows you to make very detailed maps of your field or even garden. You can map nutrient concentrations, pH, salinity, or anything else that you have your lab test for. This is very useful in precision agriculture where you want accurate data to custom apply fertilizers or lime in the exact amount needed across a field. Again, there's no real best method for soil sampling. You just have to pick the right one for your needs. Thanks again for tuning into the Science Basement. I really hope that you've enjoyed learning about soils. If you have any questions about soils or other science topics, please leave them in the comments below. I would love to make new videos to help you learn about the world around you.
Okay. That's a lot of information in about 15 minutes.
Yeah, he talks fast.
He does, and it's very graphic. Now let's talk a little bit about soil analysis. This involves most of the time, for people involved in farming, this involves collecting a soil sample and sending it to a laboratory. It's
Jim,
most
I'm
likely
an issue with the video here. 1 second, please.
the image is not coming up.
We can see you,
Yeah.
but I can't expand the view of you. It's only a small image. I can't make you full screen again. Not quite sure what to do. You guys see that? I mean, it's going to bring up more information, though. I want to make it so you can actually see it.
Does that do anything?
And I can't even bring it up. It's a Zoom window now.
The white one, the right, the big
Yeah,
one.
that's what I clicked on. It just selects the different size of the window. So. Why don't we take a quick coffee break? How about that? Yeah? All right. We're going to take a quick break while I sort this out. Sorry.
All right. I'm still connected here. It says that you are the host now.
Yeah, I'm trying to make you the host so that maybe you can control it or change it. Yeah, but it's not. So we can switch who's the main person, but I can't reintegrate it back into. Yeah, I tried. See, this is the biggest I can expand it. So it's as if he's pinned. He's the smaller. I want to make it so that he. And there's not even. It's not even giving me the options of a Zoom call at this point.
Why don't I leave the meeting and come back?
Okay, sure, let's try that. Still recording. So now, there we go. There it is. Found it.
You had it.
It was on a third screen. Yeah. So when I maximized it, it put it onto it. All right.
So you need to make only 2 screens.
Well, I can share it now again. I can split it up again. Let's see.
It's when you go there, you can just copy it. That is the second one. Let's move it to the second one. Let's see. No, there's a problem. And you go to that one, it will.
There it is. Got it. It just creates a different. I think we got it, Jim. It just creates. When I maximize it, it creates another screen on my desktop. So then I had to select it differently.
Okay.
Another 5 minutes for coffee here, and we'll get going again.
Sure.
I think we are ready to go again, Jim.
Okay. Okay, let's enter the section of our conversation today about the testing of soils. This is a very practical thing for anyone involved in farming. One of the questions that I have to introduce this section is related to your island itself. I guess it's fair to assume that you do not have a soil testing laboratory service on the island. Is that accurate?
That's accurate, Jim.
Okay. And we have shipped a soil testing kit to your project, isn't that correct?
Yeah. Yeah, it should be on the way.
All right. But in the Caribbean, there will be soil testing services on some of the other islands. The University of the West Indies may actually have a public soil sample testing service as part of their university. Have you guys checked into that before? Have you heard of soil testing laboratory services? One fellow is raising his hand, Chris.
What'd you find out?
The problem is gas is most of the time the reason for
even amongst islands. So it's shipping soil regulations. They don't want to ship something that could possibly contaminate or bring something else, island
across the islands.
Yeah,
island to island.
I sent
one other person.
I sent mine to the Netherlands years ago.
Oh, really?
Water sample and I got the result.
Oh, really? So another person sent her water and soil samples to the Netherlands and actually had results, but that was years ago.
Years ago, okay.
Three parts of the land. I think soil. Yeah.
So that's a. Yeah. Well, they're very. I mean, this is essentially a part of the Netherlands, so that's much more easy for them to do rather than from island to island. So.
Okay. Okay.
But more expensive though.
Yeah, that's a pretty long way to be shipping a soil sample.
Yeah.
It's going to cost some money.
Yeah.
Now the test kit that we shipped to you, I'm going to guess it probably has the materials in it to do maybe 50 soil sample analysis. Does that sound about right?
That's correct.
Okay. So that's quite a bit to get started. And the materials that you use for doing the analysis, the reagents, can be replenished. So after you get the test tubes and all of the physical apparatus to do the soil test, you can always buy additional reagents to expand the number of soil samples that you can test with the kit that you have.
Nice.
And so the source of the kit that you have, you'll discover that very soon when it arrives on the island. The next thing I'm going to share with you is an image of which is an example of the results of testing a soil sample. Okay, so you can see this?
Yep, we can see it, Jim.
Okay, very good.
A little small, but yeah, we can see it.
Yeah, I get it, but everyone has been sent this electronically, and you'll be able to see it in your computer. And if necessary, I'm sure Chris can provide a hard copy of the document as well. The primary purpose of providing this example is to just give you a feel for some of the type of things that are analyzed in a soil analysis. Can you see that my cursor moving on the screen?
Yes.
All right, perfect. So in this case, there are 4 different soil samples that are presented here. And the analysis, the laboratory assigns a number to each soil sample. Organic matter is one of the analysis that's utilized. And in this case, they're showing an H, an L, and an M. So they're basically categorizing organic matter as either low, medium, or high. Another type of test, phosphorus, and they have 2 different levels of phosphorus that they test from 2 different types of testing. And we'll discuss that when we get to the section on phosphorus. Potassium is also analyzed. And this one, the letters are quite small, aren't they? Yes. Down here, you have the nitrogen analysis, and these are the 3 macronutrients: nitrogen, phosphorus, potassium. And in the case of nitrogen, again, they have this is nitrates, and they have parts per million, and they categorize it as low, very low. Those are the 2 categories, low and very low in this analysis, parts per million. And we will discuss nitrogen in great detail. We will discuss phosphorus and potassium. Those are the 3 macro elements in soil chemistry with respect to supporting plant growth or crop production. Obviously, in this test, they're also measuring some essential elements: magnesium, calcium, and this is sodium. And then another measurement is pH, and we're going to spend some time discussing pH. And cation exchange capacity is a very important measurement in any soil analysis. It basically tells you the carrying capacity of the soil, the capacity of the soil sample to hold nutrients, to hold plant foods. This is called the cation exchange capacity. And these are the saturation points for different elements with respect to the cation exchange. Other micronutrients are measured here: zinc, manganese, iron, copper, boron. This is a measurement of the amount of lime that would be found in the soil. And in this case, it's low, which means that the soils are somewhat acidic. If you look at the pH measurements under this column, you'll see 4.7, 4.6, 5.2, 5.3. These are all low acidic pHs for this soil sample. Here is a measurement of the texture of the soil. And in this case, they're analyzing the sand, the silt, and the clay. They're putting a percentage on each one. And then from those percentages, you can determine the soil texture. And the soil texture is classified there are many different classifications, but the better classification for a soil texture uses the word loam. So here you have a clay loam and a sandy clay loam, a loam. Those are the 4 different classifications on this farm for the 4 different soil samples that were given. So this is a presentation, this is an example, a demonstration of what you will see in a soil analysis report. This type of measurement is very important for the farms that you're now operating. And as soon as you get the soil testing kit, you're going to begin to produce some level of data that you can utilize that will help you determine how best to manage the soils on your farm. The type of test that is coming that Chris will demonstrate to you is not going to produce as much hard data as you see in this analysis. But the data that will be produced in the soil test that Chris will present to you and leave with you will give you more of a qualitative assessment of your soils. And for example, when you see these numbers and they show a low, a very low, a low, a low, that is really qualitative information, but it is looking at a quantitative assessment, which is parts per million. The most important thing for you in reading the soil test result is the qualitative indication. In this case, it's low in this element, which is potassium. In this case, it's very low. In this case, it's low. This case, it's low. That tells us for all 4 of these soil tests, they are low in potassium. That means that for most types of crops, the crops will respond well to addition of new potassium to the field. That's what that indicates.
We got a question.
Yes.
Does the number has something to do with the low or very low? Because you see 41 as very low and then 28 as low.
So are you asking just within a single nutrient or across all of them?
No, just for potassium.
So like what's the cutoff for low and high?
Yeah, it doesn't seem to match that 41 is low and very low and 28 is low.
So they're kind of wondering, what qualifies as low, medium, high. Some of the numbers don't seem to make a lot of sense, in comparison, breaking them into that.
Right. So this particular type of measurement of the potassium salt content of the soil is in parts per million. And there's tables of information that you can utilize that is crop specific. So for example, let me start by saying that these type of soil tests can be interpreted from a very universal point of view with respect to all crops, or a soil test can be interpreted qualitatively, which is based on quantitative data, it can be interpreted from a very specific point of view for a specific crop. For example, the amount of potassium that you need in your soil to support a crop of watermelons versus a soybean crop, the interpretation of the data will be different by an agronomist or by a farm manager, depending on the crop that is being utilized in the field and the demand for that particular element by that crop. And we'll cover this a little bit more as we get into specific elements, but it is a really good question. And it is important for you to understand that not all crops need the same amount of nutrients. So when you interpret a soil test result, it's best to do it from the point of view of the needs of a crop. And this brings up a really good point also that I would like to bring out to you before we go into the more discussion about soil testing and about the various elements, is that the business of producing crops and taking the fruits, the vegetables, the grains, whatever you're producing, when you remove that from the field, your production, and you transfer that production to the marketplace, you're basically taking the plant foods, the chemistries in your soil that support the physiological functions of a plant. You're removing them from your field. It's like mining. When you're taking the element of potassium from your field, you're growing the crop. A certain amount of that potassium moves into the crop itself, and you remove the crop from the field. Let's say it's corn, watermelons, papaya, mangoes. It doesn't matter what the crop is, but you're basically mining your soils for nutrients by transferring those nutrients into the end product and removing those from your farm. A large part of farm management with respect to management of your soils and the capacity of your soils to produce crops is related to replacing those elements on an annual basis, on a multi-year basis, so that your soils do not lose the capacity to support crop production. So this is an important logistical and a rational consideration that you have to keep in mind when you're utilizing soils to support crops so that you can sell the end product. Does that make sense to you all?
Barbara, did I cover your question too?
Okay.
Hold on a second. Could you bring the test back up, please?
Yeah.
Want to go back to that questioner. They like that point. They got that, but they want to go back to that question.
Okay.
Okay.
If you look at potassium, 41, very low.
Yeah.
And 29, that doesn't
All right. Sure. So looking at potassium, for example, they're noticing that 41 is listed as very low, but yet 29 is listed as low. Could you comment on that?
Yes. You'll see here the pH number. There are complicating factors that influence the availability of an element. One of the complicating factors is pH. And in this case, you'll see that under pH, this 41 being very low is also the lowest pH. And that creates a complication. When we go into one of the areas, I'll just flash on it here really quickly. You will see that as you go down in pH, we'll come to this in greater detail, but as you go down in pH, the availability of the element of potassium decreases. That's why the interpretation of this test result, the interpretation of the result, which is what's represented here, is that the potassium, while on a parts per million basis, it's higher than the 29. Because the pH is lower, the availability of that potassium is actually less available at the low pH than it is at the higher pHs. So the requirement to compensate for potassium at a low pH, there's a greater need to compensate for potassium by adding more potassium than there is here where the pH is higher. So you might consider this a chemical mitigating factor.
Yep, they got it.
So you
Another question?
So you could do two things. I'm just thinking logically.
Sure.
That you could put more potassium inside, or you could try to make the pH high.
So they're putting things together. There's two things maybe they could do. Add more potassium or modify the pH.
Correct.
Yeah.
So that's called farm management.
Cool. Anything
All right.
else? All right, we're good.
Okay. All right. We're going to move now into these sections that you see here, where we begin to talk in more depth about what is meant by cation exchange capacity, the CEC. Then we'll show a clip on pH to help illuminate these 2 points from the soil test. And then after that, I will make some comments on acidity, alkalinity, and salinity from a farm management point of view. So, Chris, do you want to play the video clip there on CEC?
Sure. Let's see.
Not all soils are created equal, and if it weren't for chemistry, we wouldn't be able to grow many crops here, or here, or here. It's like this. Soils are composed of sand, silt, clay, and organic matter. Some have more sand, others more clay. Each soil's unique blend determines its color, texture, and storage capacity for nutritious chemicals. Although incredibly small, nutrients still need their space. And by space, we mean the area surrounding the soil's tiny particles. Keep in mind that surface area is not the same as particle size. For example, clay particles are tiny compared to sand, but they have more than 1,000 times as much external surface area as the particles in an equal volume of sand. However, if a nutrient just sits there unattached, it will likely leach out from the soil when it rains and will not be available for plants. Remember that time when you rubbed a balloon on your best friend's hair and stuck it to a wall? Well, a similar phenomenon occurs in the soil. Through their electrostatic energy, nutrients cling on to clay particle surfaces. Nutrients like calcium, magnesium, potassium, and ammonium are all positively charged chemicals, or cations. And as it turns out, most clay particles and organic matter in soil are negatively charged. So, many nutrients are positive and particles are negative. Perfect. In chemistry, as in romance, opposites attract. Good. No more leaching. But like the balloon on the wall, the nutrients are only temporarily held. In fact, there's actually a shell of water molecules that forms around the cation, preventing it from bonding permanently. This shell is often called a hydration sphere. But that's a whole other video. So, back to cations. Basically, if a plant wants a nutritious cation like potassium, it will need to exchange it for another cation or cations of equal charge. Luckily, plants produce hydrogen cations that they can exchange. One hydrogen cation for one potassium cation. Easy enough. But for nutrients with a positive charge of 2, like calcium, 2 hydrogen cations are needed. The higher the positive charge, the harder it gets to exchange or trade cations. That's because a cation with high positive charge and small size is preferentially held by the soil over those with lower charge or larger size, meaning that a large cation with a positive charge of 1 will be the first to be released. A divalent cation having a charge of 2 will be released more easily than a cation with a positive charge of 3. Whether they are held tightly or not, the nutrients are available to the plant in exchange for other cations. Not all nutrients are cations, however. Some are actually negatively charged compounds, or anions. Since anions, like nitrate or sulfate, have a negative charge, they are unable to attach themselves to negatively charged particles and, as a result, leach out when watered. Of course, all soils are different. There are soils in the tropics, for example, that have positively charged soil particles. And in that case, it's the anions, not cations, that are held temporarily and then exchanged with other anions. Most soils, however, have negatively charged particles. The more negatively charged a soil is and the more surface area a soil has, the more cation exchange capacity it has. This is such an important factor for plant growth that scientists measure a soil's cation exchange capacity, CEC, in order to help farmers determine how much and how often fertilization is needed. That's because CEC is sort of like a cup size at a fast food joint. Some soils are supersized, but others have a kitty cup. Pouring too much will just cause a mess, but if you refill several times, you still quench your thirst. Farming in low CEC soils works almost the same way. Even though the soil has lower capacity, you can fertilize more often using smaller amounts, and the plants will grow healthy and strong. And it's a good thing, too. Otherwise, we'd have very little land to farm. So the fact that farmers can grow crops almost anywhere kind of seems like superhero powers. But really, it's just knowing about chemistry.
All right.
Okay. Cation exchange capacity. You can think of that as the storage capacity of your soil with respect to nutrients. I just want to check real quick on this one. Okay, so you see these soils here in this lab report are running CECs of 19, 24, 13, and 12. And the interpretation of this is that if you look here at the texture of these soils, the first two have more clay in them than the lower two. As a result, the cation exchange capacity measurement tends to be a little higher. Another factor that can influence that is the organic matter. When it comes to cation exchange capacity, the clay fraction of your soil is where you find the majority of the cation exchange. silt and sand do not actually provide in your soil much holding capacity for cations. So if you're dealing with a soil that's a very low clay content, the probability is absolutely high that your cation exchange capacity will be low. If you're dealing with a soil that has a lot of clay content, typically, depending on the type of clay, your cation exchange capacity will be much higher. When it comes to farm management.
Got a question here, sorry.
Okay, yep.
Cation. So there's two charges of particles in nutrients. There's a cation or an anion. So it's basically a positive charge or a negative charge. Cool? All right, we're good.
Okay. From a farm management point of view, it's important to understand your cation exchange capacity because it instructs you on how you deliver nutrients into that particular type of soil. So if you have a very sandy soil and you know that your cation exchange capacity is going to be low, then if you deliver nutrients at a level that is greater than the carrying capacity of your soil, those nutrients will not stay in your soil. So you have basically overdosed your soil with respect to its capacity to hold those nutrients in the root zone. And these nutrients then can escape from the root zone, either through various mechanisms. If your soil is, one more point on farm management, if your soils are of a low cation exchange capacity, it means that it's normally more intelligent to deliver nutrients to that type of soil. Because of holding capacity, it's better to deliver nutrients in small dosages more frequently compared to delivering nutrients at a high dosage less frequent. Okay, so I'll repeat that. So if you have a low cation exchange capacity, it means that you want to make many small applications of plant food material compared to a soil that has a high holding capacity where you can deliver larger amounts of nutrients less frequently because your soil will naturally hold those nutrients and support the crop at the same time.
A question on that?
We will get into this, but if I say I see 12 or I see 24, I would not know if it's high or low.
All right, so what's a good or bad cation exchange capacity?
Well, you see in this test result, the number 19 and the number 24. Those would be considered excellent cation exchange capacities. The 13 and the 12 are very modest levels of cation exchange capacity. And when you get down into the single digits, you're dealing with low cation exchange capacities. Cation exchange capacity might be very low if you have a very sandy soil with little clay content and you have low organic matter. Cation exchange capacity is normally a measurement of the cation exchange at the surface of clay particulate as well as the cation exchange at the surface of organic molecules. So that is the range this is an example of the range of the CEC, and these numbers that are up in the 16, let's say 15 to 25 category, would be considered high, and the range of, let's say, 5 to 15 would be more modest. And once you get down below that, let's say 7 or 8 and less, you're dealing with very low cation exchange capacities, and you have to be very careful with how you manage plant food delivery in that type of a soil environment, because you may be wasting your money if you overdose that soil with plant food materials, which is a composite chemically of cation materials. Then your soil may not be able to hold it, and you may lose it. And if you lose it, you're flushing money down the drain. So it doesn't matter what source of the plant foods, what the nature of the source is. At the end of the day, when you deliver that plant food, the efficiency of that delivery process to your crop is very dependent on your cation exchange capacity for the soil. Your soil is your natural resource on the farm. You need to understand your soil as a natural resource and the dynamics of that soil from a chemical point of view. Any more questions on this CEC?
I got one actually, Jim.
Yeah.
So looking at the clay content of these soils, you know, they're comparable. And then looking at the organic matter, the soil with the highest cation exchange capacity has the lowest organic matter and about the same amount of clay as the other ones. What is there another factor that could possibly be influencing this?
Yes.
Maybe the pH?
pH could have an influence on this.
Yeah.
And you'll see the pH is quite low.
Uh-huh. So maybe making two available?
That's right. It won't take long, Chris and everybody else, it won't take long to realize that some of these considerations get pretty complex. And in the soil, everything is related. So the texture of your soil, the type of clay that you have in your soil can vary. So you can have some types of clay that naturally have a strong carrying capacity or a high CEC. One of the higher types of clays with regard to CEC is a montmorillonite clay. And so if the type of clay that's in the soil happens to be one that has high CEC capacity, you may have a high CEC measurement because of the type of clay that's in the soil. So not all clays are the same. Sand and silt, you have less chemical variation with regard to the interactive capacity of the sand and silt particulate with the chemical properties of your soil. With regard to clay, there are huge differences from one type of clay to another, and that can be reflected in measurements of CEC. Even if the soil analysis doesn't tell you the type of clay that you're dealing with, the fact that you see variations like this in CEC suggests to you that one soil sample may have a totally different type of clay compared to another soil sample. Does that make sense to you? Does that answer your question, Chris?
Yes, very well, thank you.
All right. Why don't we move on to pH? And you can play the clip there on pH, Introduction to pH.
Sure.
often hear about pH, but what is it really? It's the measurement of how acidic or alkaline a solution is. And this is important for a lot of different reasons. In water gardens, it can affect the health of our fish. In our own bodies, it can affect our health as well. Typically, you see pH referred to as a number from 0 to 14. 0 being the most acidic, like battery acid. 1 is a little less acidic, but it's still considered an acid, and this would include your stomach acids. 2 is lemon juice, and 3, we've all heard about the corrosive nature of soda pop. 4 is tomato juice. 5 is black coffee. And 6 is plain old milk. Also at 6 is your own human saliva. Now at 7, this is the halfway point between 0 and 14. And this is the sweet spot for a garden and a lot of different things. This is where pure water resides and also our human blood. At 8, we have egg whites, and these are transitioning more into alkaline solutions. At 9, we have baking soda, and 10, we have milk of magnesia, which is an antacid. So we often take this to help balance the stomach acids. At 11, we have ammonia that's used for cleaning, as well as 12, we have soapy water. 13, we have a lot of our bleaches, and then finally some of our most corrosive bases is our drain cleaners at 14. So what does all of this have to do with gardening? Well, just like our own bodies can get upset when our pH is off, so can our plants in our garden. So for more information, we're going to go talk to the expert. Dr. Zhang, thank you for joining us again. We're going to talk about pH. Can you explain a little bit of the science behind pH?
Well, I'll be happy to. pH is one of the most important tests in the routine package we talked about the last time. So pH basically is measuring the soil acidity or alkalinity in the soil. It's very important. It's just like our blood pressure. It can't be too high or too low. Basically, the acidity is the hydrogen ion in the soil, okay? It's very low, typically it's like 0.00001 molar, right? Okay. Or 10 to the minus 7. That's how low it is. Well, it's very tedious to write all this amount. So people use the symbol negative log to express that. That would equals 7. So they put a pH there, pH 7. This is how pH is expressed. Okay. In the laboratory, we do all this conversion. We tell you your soil pH is.
Okay. So you give us whole numbers to work with.
Yes. Typically, it ranges from 0 to 14. However, most plants like the neutral range, 6.5 to 7. Right. If the pH is too low, you have a very serious problem. When it's too high, some of the nutrients are not available to plants. They're like rocks precipitate in the soil. This is why we like homeowners to pay attention to pH. If there's a problem, we can correct the pH using the products available to us.
Well, and I think what you said about nutrients being tied up is kind of an important thing, because a lot of times we don't realize that we might be fertilizing, but it might not be accessible to the plant if your pH is off.
You're exactly right. You know, some of the nutrients like iron, zinc, those are micronutrients. When the pH is about 8 or 7.5, they become solids. So that's why we see iron chlorosis and other problems.
A lot of our pinnotes have that problem.
Exactly.
So if we find out we have a low pH, what do we need to do? We need to add some lime?
Well, lime is a caustic material. It brings the pH up or neutralize soil acidity. Okay. So if a soil has a pH like 5, which is low to most plants, then we add agricultural lime to neutralize it. Well, how much to apply? First of all, it depends on soil pH. That's why people need to do a soil test.
And that's on your basic soil test.
Yes.
Soil test.
Then you find the product. The product will tell you the purity of this. This is like 86%. If you need 10 pounds, you need a little bit more than 10 pounds to supply the needed active ingredients. Okay?
Okay. So you would calculate this the same way you would calculate your nitrogen needs.
Yes. People can go to the garden center, find this is the pelletized lime. Okay. Now, what is a good time to apply? Typically, it's in the fall. It takes time for the lime to react with the soil to raise the pH. So by the time you do a spring planting, the soil pH should be neutralized to the right range. So if people follow our recommendation, it's very easy to get the pH corrected.
And then we've got some sulfur here, which is what you would put down if your pH was too high.
Exactly. Most plants can tolerate a wide range of pH. Some plants, like azalea or blueberry, they can grow at normal pH like 6 or 7, but they just don't bear fruits very well. So in that case, for a serious gardener, they would like to lower the pH or add acidity to the soil. There are several products available, like alum, it's aluminum sulfate people can use to acidify the soil. But most common is this sulfur. After we put in the soil, the microorganism will oxidize to sulfuric acid. This is how to add acid to the soil to neutralize the alkalinity. Like this one has 90% of sulfur in this product. It's very effective.
You want to make sure to water these in, correct?
Yes. This can add it ahead of time. It reacts with the soil very slowly, so you need to be very patient. There's a fact sheet, I think the title is Improved Garden Soils, has an instruction how much to apply. Typically, just 2 to 3 pounds per 100 square foot. But people need to analyze the soil probably frequently to check to see the pH level. Some of the fertilizers, like this one, is labeled for azalea, also good for blueberry. The reason for that is it contains not only the nutrients like nitrogen, phosphorus, potassium, it also contains 5% of sulfur. This sulfur would act to neutralize alkalinity like this pure sulfate compound.
This might be something if you just need to slightly adjust your pH lower, whereas if your pH is more alkaline and you need to go more drastically, then you can use
Right, like these plants like pH about 5. If you have a pH at 8 right now, it will take quite a bit of sulfur to do that. And this one is not going to do the job very quickly. But if you have a pH is 5.5, already close to the target level, this may be very helpful.
Okay. You're saying a lot of people think you can add gypsum to your soil to help loosen the clay, and there's a little asterisk on this package. Can you kind of explain really what the role is of gypsum in the soil?
Well, this is another myth. Gypsum is calcium sulfate. When you apply this, it does add calcium and some sulfate to the soil. However, the solubility of this one is very low. That means it does not dissolve in water very well. So if you have a normal soil, this will not help very much at all. However, if you have an alkali soil, that means the soil has lots of sodium, high pH. This calcium will replace sodium to flocculate soil particle and then improve the water infiltration, also lower the soil pH. So in that case, gypsum is helpful. We have soil tests available to help homeowners identify if you have an alkali soil or not. Otherwise, it's not going to very help.
So really the take home is gypsum only helps if you have an alkaline soil.
You're right.
We hope you enjoyed this video. It's part of our Oklahoma Gardening YouTube channel.
What's up? You see, yeah. When you start talking to people, I've talked to any number of people where they say, "Yeah, I threw this rock dust on my garden and it just went crazy. Just add this and it'll work." It's very poor advice. You need to understand what you're doing, because you could add something and make it way worse very fast. So bringing in the soil test kit will give us some ability to start understanding soils here a little bit better. All right, Jim.
Yes. The business of managing a farm is a business of managing information. You could say that about any business, really. We're all in the information business these days. It's the new economic era, the era of information. And in the case of agriculture, the better farm managers will do a better job managing information about their natural resources on their farm, which can include and should include database of information about the nature of the chemical properties and physical properties of your soil. Understanding these properties will help you become a better farm manager. In the clip, they mentioned acidity. There are three things that you manage with respect to managing pH. We can summarize it very simply. One is acidity. So if your pH tends to run a little bit low, you have to offset that by introducing buffering agents. The most common buffering agent will be calcium-based materials. If your soils tend to be alkaline, in the case of alkalinity, you're dealing with excessive amounts of calcium in your soil. When you have a high pH based on calcium content, that means that the cation exchange sites are supersaturated with calcium cations. And in this case, acids are used to break the cation exchange sites. Calcium is removed from the exchange site, and the hydrogen ions replace that calcium on the exchange sites. What happens chemically then with respect to pH is your pH measurement will become lower, or your soils will become slightly more acidic. Low pH soils means that you have a high concentration of hydrogen ions on the exchange sites, especially on your clay. High pH means that you have a low concentration of hydrogen ions on the exchange sites. And the exchange sites are saturated with positive bases, especially calcium. Then there's also the possibility that your exchange sites will be supersaturated with sodium ions, sodium cations. And if that's the case, the soil is said to be sodic, or it is saline in nature. The farm management method to deal with a soil that's high in sodium is to replace that with calcium. And many people use gypsum as a source of calcium to replace the sodium on the exchange site. And there's a whole procedure that you follow in order to deal with a sodic soil, a soil that the calcium, where the cation exchange sites are supersaturated with the sodium ion, which is a cation. And those procedures, you may have to know those procedures at some point in the future. If, when you get your soil test back, you discover that you have a saline soil, which is a measurement of sodium in the soil. Okay, so acidity, alkalinity, and salinity are three things that you manage in farm management with respect to the pH. With respect to the pH. Now we're going to move more into the elements of nitrogen, phosphorus, potassium, sulfur, calcium, and all of the other micronutrients that are in the soil. As you can see in this graphic presentation, a color graphic presentation, which you'll have in your own computers, you can see the pH ranging here from 4 up to 10, 7 being in the middle. The green area that you see generally is the pH range where nutrients are more available. In the case of nitrogen, once you start getting over 8, under alkaline conditions of pH of 8.0 or higher, as you go higher, even if you have nitrogen in your soil, your plant cannot absorb it. On the other end of the spectrum, when your soil gets below 6.0, and your soils tend to be acidic, even if you have nitrogen in your soil, they are less available to the plant. And here you can see the influence of pH on the availability of a nutrient. The availability of the nutrient is the freedom that the plant has biochemically to absorb that element from the soil profile, from the soil chemical profile. So at high pHs and at low pHs, you see in the case of nitrogen, a very simple analysis, a very simple determination with respect to the capacity of your plant to withdraw that nitrogen from the soil chemical solution. You see a similar presentation here for phosphorus. Obviously, it's a little more complex with respect to acidity. It drops off dramatically whenever you get below 6.5. On the other hand, under very alkaline conditions, phosphorus becomes more available. Potassium, you see that above 6.0, all the way to 10, potassium is equally available. Whereas below 6, again, under acid conditions, potassium becomes, even if it's available in the soil, it's more difficult for the plant to absorb it. Sulfur, calcium, the story continues on all of the elements. With respect to pH, pH has a big influence on the ability of your plants to withdraw that sodium, to withdraw those elements from the soil. Iron becomes available at low pHs, but is not available at higher pHs. Manganese, also available at lower pHs, but not at higher pHs. Boron and copper, you see the story there for each one of them. So this information is valuable for you because when you plan your plant or soil fertility program, it's important to understand the availability of these elements to your plant from the point of view of pH. This chart will help you in the future manage your soils with respect to both the element, the availability of the element, and the influence of your soil pH on the capacity of your plant to absorb those elements from your soil. So let's see if there are any questions on pH before we move on.
Yeah, I think we got one.
Yes.
Okay.
is there, I think, something to measure the pH, right? You can like a stick and you can put it in the dirt.
So, wondering if there's some simple ways to measure pH. You know, they're talking about an example of like you see in a garden center, a like pH meter you just stick into the soil. It'll give you a reading.
Yes. Did you bring any of the pH meters from the soil lab at MUM?
No, I didn't bring anything like that.
Okay. So the next video clip will show you a soil testing process that any person can use that's very, very low cost and is available from garden centers. And if your suppliers for agricultural materials on the island, if they do not have these soil test kits available for the farmers, they should get them. And there are many examples of these types of things. They're very low cost, and they help you understand your soils better. And I would suggest that those ag suppliers have these kits available for everyone on the island. If they do not have them now, Chris, this is something that you're going to recommend to the business owners of those places. And there are many examples of this type of material that they can bring to the island, make available to the farmers, so the farmers can do their own analysis, at least producing a qualitative assessment of their soils with respect to pH, some of the macronutrients that are in the soil, and even some micronutrients. The next clip, if we're ready to go there now, you could play the next clip, which is an introduction to a simple soil test procedure. It's a show and tell.
All right, I think we're good on questions. I'll go ahead and play the clip.
Okay.
Testing your soil for nutrients gives you valuable information about your soil, which you can use to optimize plant growth and grow some really nice, healthy plants in your garden. Now, we will be using the Soil Master soil testing kit, and I'll provide a link in the video description so that you can buy this product. This product is available very cheap on Amazon. And in this kit, you will find a lot of tubes which you will use to test your soil nutrients. And this kit also has a lot of these tablets that you will see shortly. And these tablets are basically some chemicals that let you test the soil and make sure that you have adequate nutrients in your soil. Now, why do you need to do a soil test? Well, plants need three things to survive. The first and the most important thing they need is water and sunlight. Without these two things, you really cannot grow plants. Now, the third thing that you need other than water and sunlight are nutrients. Now, you can add nutrients to your soil either by adding organic matter or by adding fertilizers, whether organic or inorganic. And that's what really causes your plants to grow well and produce a lot of fruits, vegetables, flowers, whatever you may want from the plant. So doing a soil test helps you make sure that your soil has adequate nutrients for the plants to grow and flourish. So having seen the kit, let's proceed to the tests. So the first step is to take a soil sample. Now it is recommended that you dig a little bit. You find these little helpers in your soil. Just make sure they're tossed away to some other part of the bed where they can be helpful. And then take a handful of soil. And what is recommended is that the soil should be a little moist, but not wet. So this is the kind of soil that you can use for testing. They also recommend that you leave the soil overnight and then begin your test. So let's start with the first test. The first test is one of the most important tests called the pH test. It basically measures how acidic or alkaline your soil is. Now, why do we need to do that? Well, for plants to absorb nutrients from the soil needs to have the correct pH. So for example, most of the vegetables thrive when the pH of the soil is between the numbers 6 and 7. Now I'll shortly explain you what those numbers are, because you really need to have a test card or a reference card to see those numbers. So to do the pH test, you add 1 test tablet of the pH test into the testing tube, and then you add a little bit of the soil sample to it. Now when you're choosing the soil or when you're adding the soil, just make sure you don't add any wood chips or large particles. If you wish, you could sift the soil, which means that you remove the large particles and only use the fine particles. And it's also recommended that you use distilled water or at least filtered water so that the test results are accurate. Tap water contains a lot of added salts, which might give you a false result. Now, once you shake the solution very well with the soil, you let it stand for a few seconds, about 30 seconds to a minute. And once the soil settles down, you need to match the color of the solution on the top with the pH level. So as you can see here, the pH level is a little bit towards 6, as you saw in the picture. Now let's take a soil sample from another bed. And remember that if you have multiple areas in your garden, you need to do 1 test per area. And let's wait for the solution to settle down. It usually takes about a minute for the soil to settle down. And here you can see when we measure the pH level, it's about 7, which is again ideal. So as long as your pH is between 6 and 7, you're good. However, some plants do like higher or lower pH. Now, changing soil pH is very easy. You add garden lime to make the soil more alkaline and sulfur to make the soil more acidic. Now, remember that some plants do prefer acidic soil, like blueberries. So be careful what you're doing. So let's now jump to the nutrients test. The first nutrient we will test is nitrogen. For preparing the test solution, dissolve 2 Flock-X tablets in the water and then add the soil. The Flock-X tablets let the soil settle down towards the bottom of the cup so that you can use the clear solution that's on the top to do all the tests. So once you dissolve the 2 tablets and the soil settles down, you will be using this solution for the rest of your nitrogen, phosphorus, and potassium tests. We will now add the nitrate test tablet to the testing tube. Now the solution that we created earlier will be used for all the 3 tests. So make sure you save the water from the previous test. As you can see here, we need to reach the mark that is there in the tube. And once that mark is reached, just make sure that you have just enough water, and then make sure the solution is really well mixed. And once this settles down, you can measure the level of nitrogen. And as you can see here, it's very low. It really matches the low nitrogen level. And this is a very true indication of the nitrogen levels, because most California soils, for example, are deficient in nitrogen. So you need to make sure that you have adequate nitrogen in the soil. So as you can see here, these are the ways to add nitrogen to your soil, and your plants will really benefit from that. Some of these are organic sources and some of these are inorganic sources. And whether you want to use organic or inorganic fertilizers really depends on your choice. The plants do not distinguish between either fertilizer types. So the next important nutrient that plants need is phosphorus. Now let's go ahead and do the phosphorus test in a similar manner. And then you can see here the chart now corresponds to phosphorus that's quite high. So our soil is really not deficient in phosphorus in this case. And remember that you need to test soil from various locations in your garden to arrive at any conclusion. Now, if you do find your soil deficient in phosphorus, which is essential for flowering and producing bulbs, you need to make sure that you either add bone meal, manure, rock phosphate, or superphosphate. Once again, whether you use organic sources or not is entirely up to you. You are the best judge. And the final nutrient that plants need is potassium. And in this test, you can see that the level of potassium in our soil matches high, which means that we have adequate potassium levels. Now note that most soils will have a lot of potassium and phosphorus. It's nitrogen that most of the soils lack because plants use a lot of nitrogen when they grow. So with this soil test, you can really make sure that your soil has adequate potassium. It's really good for growing plants that produce a lot of roots and tubers. And here are the common sources of potassium that you can add to your soil. Again, some of these are organic sources, some of them are inorganic sources, and both of them work really well for growing your plants in your garden. So there we have it. That's our soil test results. And I hope you like this video, and I hope this encourages you to do a soil test. If you're not getting success in your...
Okay. So Roland, you said that there is a test like this available on the island?
We did this test, we got a test in Birmingham. We did it at Chelsea Space. The pH was 7, but the electromagnetic.
So it was just like this?
Just like this.
Okay, so it is available here at one of the big box building stores, so to speak. So
great. So yeah, I'm not surprised. This you find in garden centers and people who have flower gardens. This is a common product that's out there. And I would suggest, Chris, if this is available on the island, then why don't we try to get a kit for each farm? Normally these kits allow you to do a handful of tests, like maybe 10 or 12 or 20. I would get one of these kits as soon as possible so that you can, it'd probably be a good idea to work as much as possible with the kind of resources that are already present on the island.
yeah, sounds good. All right, I'll check it out.
Now, obviously, as you can see in this test, it's a colorimetric graphic presentation that gives you a feel for whether the pH or the elements are in a low, medium, or high position. But all of those qualitative assessments are actually based on hard quantitative measurements, because what you are doing when you execute this test is you're creating chemical reactions. And then because the chemical reactions reflect color, which is a reflection of light, that you're able to present the data qualitatively with color. But what is actually being represented are parts per million within a certain range. And they've summarized that range for you colorographically so that it's easy to interpret the data. But what's actually being measured there is a byproduct of a chemical reaction that pulls the elements off of the cation exchange, so you can see the saturation point on the cation exchange with respect to the specific elements. All right? So while it looks very simple and very qualitative, it is based on quantitatively measurable chemical reactions. And that's the purpose of the reagent. That's the little pills that he was putting in there in the water. And when you get the soil testing kit, there will be instructions with it. Pretty simple to use. How many here in your group have utilized a soil testing kit like this? One?
2, 3 people.
Anybody else?
Four
Two
people. So,
all right. So some of the people have already had some experience with this. It would be good to give the experience to everyone in the class, Chris, and I know that you are intending to do that.
Yep.
Okay. So moving along, let's go to the next clip and take a quick look at the mechanism, which is a chemical mechanism, which we're now going to enter the world of the interrelationship between plants and the soil chemistry. The soil chemistry being largely, when you think of chemistry, you have to think of chemical reactions, which is often talked about as the interactive capacity of the soil composition. That fraction of the soil mineralogy which is interactive or is subject to chemical reactions is largely the clay fraction of your soil. That's where your cation exchange capacity is concentrated. So this next clip will illustrate to you in a very simplistic way how one element, the element of iron, is pulled from the cation exchange site into the plant's internal chemistry. So why don't you play that clip so we get a little feel for how plants assimilate elements from the soil profile.
Not all soils are created equal, and if it weren't for chemistry, we wouldn't be able to grow many crops here
or
here.
No?
It's the same one we just now.
Yeah, let's see. Cation. Introducing plant uptake of nutrients, right?
Yes.
It's linking to the
Not
cation
also-
exchange capacity.
Okay, just a minute. Yeah, I see that. Okay. Okay. What I would like to do now, Chris, we'll come back to that, and it looks like the link, and I'm not sure why, is not correct, and I'll correct that.
Okay.
But let's take a look at the time frame that we're in right now, and we are 25 minutes from the end of your presentation, end of your time in the class.
Yeah. I think people it's been a lot of information, I would think.
Oh,
So,
yeah. Where we're at now is we're beginning to enter the discussion about elements, first starting with nitrogen. The discussion about nitrogen is a very, very important discussion. It's one of the most intensive elements of managing soil science, managing soil chemistry on your farm, is the management of nitrogen. It's one of the most limiting factors with respect to growing crops. Your understanding of how nitrogen is managed on the farm is going to be very important to you. Understanding the dynamics of nitrogen in your soil intellectually in farm management will be a very important part of your skill as a farm manager. So I think it would be good, Chris, just to pause here, and at the next session, we'll start with nitrogen, and maybe we'll correct a clip on how plants take up nutrients, which is a very short clip, five minutes. But the discussion about nitrogen will be a lengthy discussion, and we'll take that fresh at the first part of the next session. How does that sound?
Yes, that sounds great. Sounds great, Jim.
Okay. Any final question before we dismiss today?
No, I think they have plenty to think about.
Okay, well, you have to realize that when a university student goes through a full semester on soil science, an introductory level even at soil science, they take 3 months to study all these topics. You guys are so far advanced as students that we are assuming that you're going to be able to absorb most of this in 3 days.
They say, of course they can. Yeah.
Yeah. So it's a pre-drawn conclusion that this will be the case for all of you. So we'll hit it next time, and we'll take off on nitrogen, and it will be a very interesting topic for you to discuss with us. Okay, Chris?
Yeah, sounds good, Jim. Thank you.
All right. I'll be in India for the next session.
3 o'clock, right?
It'll be 3:30 in the morning for me from India, yes.
Wonderful.
But 6 o'clock for you. 6 o'clock for you. India's on a very odd time difference. But 3:30 for me, 6 o'clock for you.
All right. Well, appreciate
All right.
it. We'll see you next time.
All right. Adios.
Bye.